Welcome to required practical number 9, light. This is a two-part required practical, first looking at the laws of refraction and then looking at the laws of reflection. Before we begin, let's just make sure that we understand the terms that we're going to use in this investigation. For the part of the experiment where we look at refraction, we need to use some kind of glass block or something that we can shine light through. Now, you might have your glass block as like a D-shaped glass block or a square-shaped glass block like this. And you can do it with either. And you might have to do it with both, in fact, because you might have a D shape in some materials but a square shape in others. So you need to know how to do it for both. Now, with either of these, the first thing to do is you're going to place it down on your sheet of paper. And then you're going to draw around the shape so that later you know where the shape was. And if it accidentally moves, you can put it back again. The next thing you need to do is you need to draw a normal line. And so I'm going to draw a normal line on both of these. The key thing is that it has to be 90 degrees to the surface. So 90 degrees, and it's going to go from the outside of the glass block in the glass block. So I'm going to have to pick up my glass block from the piece of paper, draw my normal line, and I can use a protractor if I want to be really accurate, and then put my glass block back on top of my normal line. Here again, I can do exactly the same on my D-shaped block. So here is my normal. Now my normal is really important. It is against the normal that I'm going to measure all of my angles going into the material and refracting through my material. So here, what I'm going to then do is I'm going to get my light source, in this case a ray box, and I'm going to shift it across the desk until my ray of light intersects with the point where the normal line that I've drawn goes into the new medium. So for example, if I got my ray of light and I drew it coming in here, then what I would do is I would mark on my piece of paper with another colour a couple of little X's like this, an X here and an X here. I'd take my glass block off again, and I would then use a ruler to connect those little pencil marks so that I could draw my line on, so that I know where my ray of light is going. It's not complete yet though, because all rays of light being drawn with a ruler also need an arrow to show the direction. Don't forget the arrow. So in it comes, and you can draw it anywhere, but I would avoid putting it down close to the normal line because I'm going to want to draw angles here slightly later. So then I put the glass block back on again, and what I note is that the beam of light will go through the glass block, but I can't mark on the paper underneath the glass block without moving the glass block. So what I have to do is I have to mark just down here where that ray of light is emerging, and say that it emerges just here. I then remove my glass block again, and what I have to do is I have to join the point where the ray of light entered the glass block and exited the glass block, and I can join them up with a line that I have then drawn onto the piece of paper. Again, it's nice to have that arrow there representing the direction that the light is going. Now there are some angles we're going to have to measure on this thing relative to the normal. There's the angle of incidence. This here, given the symbol I, is the angle between the normal line and the incident ray, the ray going into the medium. And this angle down here between the normal line and the refracted ray is called the angle of refraction. Now within this experiment we're going to use the angle of incidence and the angle of refraction to work out the refractive index of this material, the extent to which this material slows down light. On a D block it's very similar. We're going to do the same thing. We'll put our light beam in so that it hits the intersection of the normal line and the boundary into the glass, and you do exactly the same by basically marking on with a pencil 2 points and then taking the glass block away and then using a ruler to draw that straight line. When you're asked to describe this experiment, remember these parts of the process, because quite often students will say things like, you know, just put a glass block there, draw a line through. You can't draw a line through while the glass block is there. So you're going to talk about the process of marking where it is and then moving the glass block and then connecting the dots and then putting the glass block back again. Now what I might find is that, just like with a square block, the light is going to emerge somewhere and then I need to mark out where it's emerging onto the paper, take the glass D block away and then connect the dots. Now I'm not bothered about what's happening down here, that's for another time. And here, like before, we have the angle of incidence and the angle of refraction, both of which I need to measure with a protractor. This experiment requires accuracy, so a nice sharp pencil and a ruler with your piece of paper are a must. So I'm now nearly ready to begin. I've got my ray box and I'm going to plug that into this power pack over here, and we're going to set the voltage at an appropriate level, not so high that it gets too hot but not so low that it is too dim. And then what we're going to do is this is the first object we're going to use. It's a glass rectangular block. We need to first of all place it square on our piece of paper and then draw around it so that if it moves we can put it back in place. Now, there we go. Now what I want to do is I want to make a point here that is going to be where my normal line is. So using a protractor, lining it up with that point there, I can very accurately draw a really good normal line. And so this normal line is exactly at 90 degrees to the surface. There we go, there's my normal line. I'm going to place the glass block back exactly on top, being careful to be accurate. Then I'm going to turn on my ray box, which should turn on. But it's not turning on. Okay, I don't know what was wrong, but it is now turned on. And you can see that the ray of light is too faint to see. So you need to consider doing this in a dark environment. In this lab here, we have the ability to turn all of the lights out. And we're going to go into the dark in a minute. Before I do that, I want to show you how I'm recording my results. It's always sensible to draw a little sketch of what you're doing. So if you came back afterwards and you needed to think about the process by which you came to this data, there's a little memory aid of exactly how you'd set it up. I've got a table here, the substances that I'm going to test, the angle of incidence in degrees, the angle of refraction in degrees, and the refractive index, which I'm going to use this equation to work out. In the dark, you're not going to see as much on this video, but we're going to do it anyway. So we're now in the dark, and all I'm going to do is I'm going to just move this to some angle. And what I want to do is just make sure that the cable is not moving around. This is perfect. So I've got it intersecting with the point where the normal enters the glass block. And I'm going to mark with X's on my piece of paper, first of all where that initial line goes, then over here where the line is appearing to come out. Then what I can do is I can take off my glass block, and the rest we can do with the light on. You may have to continue to work in the dark if there's more than one of you doing it in the room. But for the sake of this video, the light has come back on and I am connecting the dots. So I've connected the dots for the ray going in and the ray coming out. What about going through? Well, we use this point here and that point there, and we connect them. You'll notice that refraction has been seen in the glass block. It has refracted towards the normal. And so now we are going to measure the angle between the normal line and that line. And so the angle between the normal line is, well, the easiest way to do it, I suppose, is if we align it like that, because then the scale on the outside edge of the protractor is here. And you can see that it goes up to 45 degrees. So the angle of incidence here is 45 degrees. What about the angle of refraction? Well, here you can see that it is 20 degrees. And so the first data point here on my table is that for glass, it was 45 degrees going in and it was 20 degrees coming out. So what next? Well, the next thing I want to test is this. This is acrylic. So it's a kind of perspex. So this perspex, I'm going to do it with a new sheet of paper. Put that to the side. There's a new sheet of paper on my board. And I'm now going to repeat the process, starting by drawing around the shape. So here we are in the dark again. I've got my ray of light hitting my D block, and I'm going to draw on 2 X's before and 2 X's afterwards. I should have them further apart actually to increase the accuracy. Take the D block off, and we're going to place a ruler like this, connecting the dots. This section here, between here and here, again, we're going to connect it. Now what you can see with the D block, which is a part of its design, is there's no refraction seen at this point where it is leaving the block because of the curved surface. But we do see refraction over here. That is what we need to measure. So again, we're going to go in there, and we need to make sure that our line is long enough so that it can actually be seen. But where we have this, it is at 27.5, let's call it 28 degrees. That's the angle of incidence, and the angle of refraction around is equal to 20 degrees. So the next data point for perspex is that it went in at 28 degrees and it came out at 20 degrees. Now we have to make some choices. We want to find the refractive index of more materials than just these two. The problem is that in most laboratories these are the only two that we have, glass and perspex. What you can do is you can delve into the refractive index of certain liquids, and I'll show you how. Here we have a dish, like a Petri dish, that is exactly the same dimensions as the D-shaped glass block. Putting liquid into this dish will enable us to measure the refractive index of those liquids. So these are the liquids that we have. This is water. This is 40% water with sucrose. And this is propan 1,2,3-ol. So these are going to be different. So we'll start with the water and we'll see how we go. Now an important thing here is we draw around it before we put the liquid in, because we don't want it sloshing around all over the place, especially in the dark. So here we go, I've drawn around my shape. Just as before, we'll set it up. So in goes the water. And it's quite faint, but we can still see it. So here are the X's going in, and here is the ray of light coming out. What's really obvious with the light on is that in the dark it's really hard to fill this up without it overflowing. So we've got to try to carefully get it back in there. So that was the water. We must dry this before we do any other liquids. So again, I'm going to join the dots. And there we go. So what we have is a refractive, an angle of incidence here of 27 degrees, and an angle of refraction here of 22 degrees. Okay, so we'll record that. Water. And so it was 27 and 22. So now the sugar solution. This is really sticky. If you're having trouble seeing the light ray, you might want to turn up the brightness. I think we can see it here. It's emerging there. There we go, it is there. It is just really faint. And the ray of light going in here. Okay. Ugh, and so sticky. Alright, so again, light ray coming in, light ray out, connect the dots, measure the angles. So here we go. First angle, the angle of incidence is 24 degrees. The angle of refraction here is 20. And record that here. So sugar solution, and we had 24 going in and 20 coming out. One last one to do, the propan 1,2,3-ol. This is going to be different. So here, the propan 1,2,3-ol, otherwise known as glycerol. Ooh, syrupy. In it goes. This is going to be interesting. So here is my line going in. Here is my line coming out. Just spill it everywhere. Back in there. And this is going to need a good washout before it is used again for anything. Glycerol all over here, so you have to be kind of careful. I'll try to draw this on without getting in a mess. You can see it there as well. Join the dots. And there we have it. So let's measure some angles. We have an angle of incidence of 25 degrees. And we have an angle of refraction which is equal to 19 degrees. Now this is the final piece of data that we need. So glycerol, it was 25 and 19. Let's go calculate our refractive indexes. So let's calculate some refractive indexes. We're going to use this formula here, sin I divided by sin R. These functions here require our calculator to be in degrees, so check that yours is. One thing to note though is that if you do sine 45 divided by sine 20, it produces an incorrect answer, because what it's done is it's done sine of 45 divided by sine 20 close brackets. You need to put an extra bracket in after that first angle to get the correct answer. So instead we want to do sine of 45 close bracket divided by sine of 20 close bracket, refractive index of 2. You always expect the refractive index to be no smaller than 1 but no greater than about 3. So here our refractive index is 2.0 0.07. We'll do the next one. Sine of 28, close bracket, divided by sine of 20. A 1.37. Next one, sine of 27, close bracket, divided by sine of 22 is 1.21. Next one, sine of 24, close bracket, divide by sine of 20, close bracket, 1.19. Finally, the last one, sine of 25 and divided by sine of 19 is 1.29. Oh yeah, actually it's all going to round up, so it's going to be 1.30. Refractive index doesn't have a unit. It is just simply the ratio of how fast the light is travelling in this substance compared to the speed of light in a vacuum. Now this concludes the first part of the required practical, but there is a second part, so let's have a look at that. What I'm going to also do is I'm going to draw a normal line onto my mirror. Now I would do this like before. I would draw this onto a piece of paper and I draw around where my mirror is so that if anything moves I can put it back again. And then what I'm going to do is I'm going to move my ray box so that incident ray intersects with the point where the normal hits the mirror. Now of course it could point anywhere, but I want to measure something. So I want to send it in to that spot. I would do it by putting a few small X's on the paper and then moving the apparatus out of the way and then joining the dots with a line. And of course it's not a ray unless it has an arrow. Of course what's going to happen is that ray of light is going to hit the mirror and it's going to reflect off. So similarly I'm going to draw here, I'm doing this freehand but we can do it accurately with the actual apparatus. I would mark the reflected ray and then draw the line through it. I'd be curious as to this angle, the angle of incidence, and how it compares to this angle, the angle of reflection. Now be careful here, we've already used the notation R in the case of refraction to represent the angle of refraction. This is different. This is the angle of reflection. Let's go and have a look at the equipment. Now your apparatus might look like this. Here we have a protractor that is built into our mirror so that we can measure directly the angle going in and then using the point where the 90-degree line touches the mirror is the normal. Or we could do it with a freestanding mirror, draw around it, draw a normal onto it, and then shine the light in various different places. So what we're going to do is we're going to do it with both so that you can see. So we're going to turn on our light ray and we're going to shine it in here. Of course we need the light off. Before we do turn the light off, let me show you what I'm going to record for this. I have got a table. I want to collect 6 pieces of data and I have the angle of incidence and the angle of reflection. Quick diagram, let's go. So first things first, I'm going to draw a line to represent the back of the mirror so that if it moves, I can move it back. I'm going to start out with my incident ray going straight down normal so that the angle of incidence excuse me, is equal to 0. When the angle is equal to 0, you can see the ray of light is reflected straight back again. So the reflected angle is also 0. But now I'm going to rotate this, so it is now going in at 20 degrees. And you can see that it is now coming out also at 20 degrees. So my second reading angle of incidence of 20, the angle of reflection is 20. The next, we're going to have an angle of incidence. Now you see my paper moved, but that's okay. I can move it back. My angle of incidence, so that was 10, 20, 30, 40. Shining in at 40 degrees, and it is shining out at 40 degrees. I can rotate my paper as well as rotating my light source. So 10, 20, 30, 40, 50, 60. Let's go in at 60 degrees. We read it off, and it is coming out at 60 degrees. And so now we're getting at quite an acute angle. I'm going to pick, let's go with 75 degrees, and this is coming out at 75 degrees. They don't have to be equally spaced. My data points, they can be whatever I choose. And then right up at 80 degrees, and it is coming out at 80 degrees. So here is my data. What you can see is that the angle of incidence is always equal to the angle of reflection. If we shine it in at a greater angle, it reflects out at a greater angle. In fact, this gives us the law of reflection. The law of reflection is that the angle of incidence is equal to the angle of reflection. One final part of this investigation asks us to look at what happens when light reflects off different surfaces. So I have here a plane mirror, a glass block, a metal block, and a wooden block. And we're going to see what happens. Now, this part of the investigation, we're not going to take measurements, but we are going to record our observations and take note of how we do the experiment. So first things first, the mirror. The mirror reflects a beam of light following the law of reflection. This is known as a specular reflection. What happens with the glass block? Well, what we find is that it also reflects off its front surface. It's faint because some of the light is actually going through the material. Not all of it is reflecting. But what we find is more and more of it reflects when the angle of incidence becomes really large. This is one of the reasons why when we walk up to a puddle, when the puddle is far off, we see the reflection of the sky, because we're looking at it with very large angles of incidence and reflection. But as we get to the point where we're looking almost directly down on it, we can now see the bottom of the puddle. It's all to do with the changing position, the changing angle of our observation. What about a piece of metal? You can see that a shiny piece of metal also reflects the ray, but you notice that the ray is becoming more diffuse out here, it's spreading out. And that's because the surface of the metal is not perfectly smooth. It's almost smooth. It can produce a specular reflection, but it is actually scattering some of those rays of light, and so it is slowly spreading out. A more extreme version of this is what we get with wood. And what you can see here is that the light hitting the wood is now spreading out all over the paper. Let's take a photograph of that, and we hopefully will get a better view. So here you can see a long exposure photograph showing that the ray of light has not been reflected in an organised way, but is instead the light has been scattered in all directions from the surface of the wood. This is called a diffuse reflection, and it is by this mechanism that we can see most objects in the room around us. If you would like a copy of the data, take your screenshots now. This is for the refraction experiment. This is for the reflection experiment.